এখন একটা মিটিং আছে, এখন কথা বলতে পারবো না।
Hello, sir. Am I audible to you?
Yeah.
Okay. Uh, Good morning, everyone. Our next session will be delivered by Professor Debasish Bandyopadhyay, sir, on advances in earthquake engineering and dynamic analysis. We all know what has happened 2 days before in Turkey and Syria, so the importance of this topic is very high. And first of all, please allow me to introduce Professor Debashish Bandyopadhyay, sir. Uh, Professor Debashish Bandyopadhyay sir received his BE in Civil Engineering from Jadavpur University, Kolkata, India in 1987. Subsequently, he did his MTech in Structural Engineering and PhD from the Department of Civil Engineering from Indian Institute of Technology, Kharagpur, that is IIT Kharagpur. He joined Damodar Valley Corporation in 1987 and associated with different civil and structural construction works of major thermal power project, including the Railcom PSC road bridge over River Damodar at Raniganj. He joined the Department of Construction Engineering, Jadavpur University, Kolkata, India in 1997. He went to the University of Arizona, USA for advances research in earthquake engineering during 2005 and 6 after being awarded national fellowship from MHRD Government of India. Presently, he is a professor and former head of the Department of Construction Engineering, Jadavpur University. He is the founder coordinator of master degree program on structural repair and retrofitting engineering in the Department of Construction Engineering of Jadavpur University. His research interests are structural health monitoring, computational mechanics, earthquake engineering, conditional assessment of concrete building and bridge, seismic evaluation, and retrofit of structure. He has published more than 60 papers in international journals and conferences proceedings. He has guided 3 PhD theses, 36 MTech theses, and presently 8 PhD students are working under him. He is the reviewer of International Journal of Structural Integrity. He has examined many theses of IIT Kharagpur, IIT Varanasi, IIT Dhanbad, IIEST Shibpur, and many more reputed institutes. He was a member of different advisory committees like ISI Kolkata, SNBI Kolkata, Kolkata Mathematical Society, INWDT, Government of West Bengal, and at present of IIT Kalyani and Bridge Advisory Committee, KMDA, Government of West Bengal. He has delivered several invited lectures at various reputed academic and industrial organizations like IIT Kharagpur, IIT Roorkee, IIT Bhubaneswar, IIT Varanasi, BITS Pilani, Tata Steel, DBC, Ultratech Cement, Sham Steel, Indian Concrete Institute, etc. He is a member of Technical Committee of Repair and Retrofit of Concrete Structure of ICI and nominated member of BIS CED 39 Earthquake Engineering. He has provided structural consultancies on building bridges, industrial structures of Tata Steel, DVC, Cognizant, OTPC, SAIL, BPC, BPSCL, PCT, SDB, PWD, NBDD, Government of West Bengal, US, UDSD, Government of Sikkim, etc. He is a member of few professional bodies like IE, IERC, ICI, Society of Prevention of Kolkata. He was vice president and presently one of the governing council member of Indian Concrete Institute ICI. This is about the Professor Debashish sir, and if I continue, it will take the whole day to introduce such eminent personality. And we are very fortunate that such eminent personality is going to deliver the session for us. Now I request Professor Debashish Bandyopadhyay sir to continue with the session. Sir,
Mm.
am I audible to you?
Yeah.
Uh,
Thank you very much for the introduction.
it
Uh,
will take the whole day, sir, to introduce
no,
you.
no, it's I am not so much thing, but there is a lot of words written there.
Yes, sir.
Uh, Thank you very much.
Yes, sir.
Uh, Good morning and welcome all the participants. Actually, I do not know, but what are the backgrounds of participants, but I shall try little bit of uh, normal earthquake engineering along with some advances, including some dynamic analysis. You can see the pictures. These pictures are one from Bhuj earthquake, and the middle one is from 2011 Sikkim earthquake. We from the university did a lot of seismic evaluation during the Sikkim earthquake. And yesterday, on 6th February, while I am thinking that I have to deliver the lecture, another big earthquake, major earthquake of 7.8 Richter scale happened in Turkey. So the contents includes introduction. I will go through little pictures of the Turkey earthquake yesterday. Then what do we mean by seismic disaster mitigation? What are the important consideration of earthquake or seismic activity? That is the characteristics of earthquake, different hazard levels and performance level. Then the role of ductility, both for concrete RCC structure as well as to some extent to the steel structure. Then some of the advances in the last uh, codal revision 2016, that is IS 1893, what are the impacts of those revision? I will go through little bit of numerical study by one of my uh, MTech student. I will also touch upon seismic evaluation and retrofit as per Indian standard code and the concluding remarks. Now, this slide is very common to me, but at the same time it is very close to me. You see, earthquake is a very low probable event. Wherever you are staying, the probability of occurrence of earthquake like this magnitude of 7.8 or 7, whatever may be, it's very low. But why we consider earthquake engineering to that extent? Because the consequence of an earthquake is tremendous. What we can see in the morning newspaper or whatever news channel, that Turkey and Syria, they have been devastated. USGS has predicted that more than 10,000 people will die. Till now, 2600 dead report has came. But they predicted that there are a lot of bodies inside the debris, so it may go up to 10,000. So within a fraction of minute, 45 seconds duration was the first 7.8 Richter scale yesterday. So with these 45 seconds, 10,000 people have lost their life and a lot of economy. It is yet to be estimated has gone. So regarding the consequence of earthquake engineering becomes so popular that I always give an example that we never go for insurance while we are traveling by car or by bus. While we're in train, now there is a provision for going for insurance, but sometimes we do, sometimes we do not do. But in case of flight, insurance is a must. Now, why? The probability of accident in road is much higher than the railways, and finally the aircraft accident is very low. But still, the insurance is becoming almost mandatory only because that if there is an accident, then the conditional probability of death or this probability of survival is very low. So like earthquake is also earthquake, the probability is low, but the consequence is high. Why earthquake causes? That is a geological thing, but most of the people adopted that it is the theory of plate tectonics. But we, the civil engineer, we, the structural engineer, are more uh, uh, cautious about the effect of earthquake, that is the structural damage, including loss of life and loss of economy. Now, if we see the last few decades, like many other hazard, earthquake hazard or seismic disaster is also increasing day by day, and they are devastating in nature. Now, we got one project from Tata Steel that why the underdeveloped countries have suffered so much during an earthquake disaster, not the developed country to that extent. And when we studied, that was a only study based on the literature. When we studied and we have compared all the codal stipulations of different countries, there is no direct or very straightforward relationship between the losses with the magnitude, intensity, etc. But they all have it's a multi-function, multi-variable problem. Yesterday, Turkey earthquake, there is a very important features, the focal depth. If the focal depth is very low, the chances of devastation or the chances of disaster is much, much more. So there are a lot of things, including geological, geotechnical, because sometimes wave will attenuate, sometimes wave will amplify, depending on the geotechnical properties and structural aspect. And then it is further aggravated with the governance and awareness criteria. If we see Japan or USA, they are much more, even New Zealand, they are much more stringent and they are practicing the earthquake consideration in a much more strict way. Therefore, the hazard or the disaster is very low compared to Turkey, or you can go for Haiti or our India, etc. Now, this is a curve by Wilhelm. If you see earlier days up to 1900, the loss in terms of cost is very low, but it is a increasing day by day and 10 times increased during the last 100 or 120 years, and it is again going in a upper slope. Now this is a common slide many people have seen before, that due to the subduction there is a faults creates a huge amount of energy that releases, and based on the location of fault there are hazards, and with the development of our society, of our infrastructure, etc., that is the exposure. You see, long back, say 1,000 year back, there is a lot of earthquake, but there is no such death or loss, because at that time the exposure or the built environment is not to that extent. So while we are developing our society, particularly the civil engineers, increasing day by day by the infrastructures, that is the exposure to the hazard. So vulnerability will go high. So our role must be to protect those structure, whatever we have built, according to the seismic demand. So structure should not be built. Any structure, if we build without the seismic consideration, it may be treated as non-engineered structure. Now coming to the yesterday earthquake, you can see at the early morning around 4:15 or something, there is a first earthquake of 7.8 Richter scale, which is 18 kilometer focal depth. That means the epicenter is at the surface of the earth. So the hypocenter or focus of the earthquake is 18 kilometer below the earth crust. And there are a lot of aftershocks, including one in the noon that is of 7.5 magnitude. It is in the south of Turkey, and people are now telling that either the East Anatolia fault zone or the Dead Sea transform fault zone, they are responsible for this triple junction Anatolia, Arabia, and African plates. So huge devastation, it is yet to be estimated, and I will show few pictures collected from the internet. This is one picture you can see. It is one structure or building has collapsed like pack of cards, and there is a lot of debris. Many bodies may be inside. And just I'm showing some videos that is sent by one of my students to me yesterday, collected from no doubt internet. I think within a very few seconds, the structure, the buildings, they are collapsed like a pack of cards. There is another video. I think you may have seen this, but still,
Aman yarabbi aman, aman yarabbi aman. İçeride insan var ya, niye çıkmadınız? Allahu Ekber. Bırak abi. Ya gerizekalı. İnsan var dışarıda. Ya dedik ki çıkın dışarı. İnsan vardı.
You can hear the cry, the, the huge scale devastation that took place yesterday.
Buradaki halk elini uzatabildiğine yardım etmeye çalışıyor. Lütfen yardım gör denir. Kahramanmaraş'ta durum çok...
And I can share uh, one of the sentence told by Professor Sudhir Jain, one of the pioneer in spreading the earthquake engineering throughout the country. He said after the Bhuj earthquake that it is not a natural disaster. If it is a natural disaster, then along with the people, there should be the death of other creatures like monkey and etc. etc. But not a single monkey died in the 2001 Bhuj earthquake. So why more than 20,000 people died? Because of our incompatible buildings or structures that we have built. They are not able to withstand the earthquake demand. So it is our moral responsibility and duty that our structure should be adequate earthquake resistant. These are few pictures from the Turkey and Syria earthquake. You can see now there is nothing. People are searching for their beloved one. The top one in Turkey, you can see that in a Syria village, this was the structure, and you can see the structure is not a very tall story structure. But after the earthquake, everything was destroyed like anything. So the devastation power of earthquake is manifested by only yesterday. These are few pictures. There is a playground around. There is a lot of structures. Now this becomes a debris. Many people have died due to the collapse of buildings. And concrete, I am also from Indian Concrete Institute. Concrete, no doubt, is a very popular construction material, and people are consumed after water. Is second thing is concrete, but concrete has certain good properties. But at the same time, we must use concrete in such a way that the earthquake vulnerability is reduced. That is the intention of earthquake engineering. There are a few videos I am not going to show. These are few pictures. You can see the total city was devastated like anything. I don't know whether it is clear from your uh, monitor or not, but you can see that there is a lot of destruction. This is progressive collapse in Syria. Uh, like a pack of cards, they have collapsed the buildings. The top story was totally destroyed. You can see wherever there is a balconies or wherever there are big openings, they are the uh, vulnerable point during an earthquake. So if we increase the indeterminacy or redundancy in the structure, and if we are bound the structure in such a way that the uh, panel length is reduced, then the resistance against earthquake will be increased. You can see more pictures. So now I will stop the devastation of yesterday's earthquake that was only collected yesterday. You can see the power of earthquake up to 7.8 Richter scale yesterday. This is also one interesting video. That's why I have put this one. The non-structural element, you can see the non-structural element of this building. The facade of the tall story. During the earthquake, you just see what happens to that facade. And anybody below that facade may have been died. The structure is still standing, able to withstand the earthquake, but the non-structural element, that couldn't bear the earthquake shaking. Now, that is also very important issue, that not only the structure but the joint between the structural and non-structural element also plays a significant role, including electrical cables, everything, because sometimes secondary hazard like fire, etc., is a result of earthquake shaking. So, with this very recent background of Turkey and Syria earthquake, let's see what do we mean by seismic disaster and its mitigation. Disaster means a destruction and widespread damage. It may be natural, may not be natural or man-made, but ultimately the effect is a negative effects on life, property, etc. And disasters are manifest as hazard. Then there are a lot different type of natural hazards, but the most common three disasters are due to cyclone, due to flood, and due to earthquake. And the red one indicates the loss of life, the blue one homeless, and the violet one is the economic loss. Now see, in case of earthquake, all are very, very significant amount. So loss of life, loss of homelessness, and economic loss, whatever we have seen in the earlier pictures. And whatever Professor Join said, I just formulate the sentence that due to the incompatible design and construction to the seismic demand, most of the structures, particularly complex structures, they collapsed. So it may not be fully natural. The event may be natural, but the disaster are caused due to our fault. If we compare the Asia Pacific region with the rest of developed country, the loss of life is more in case of our countries compared to the rest of life. And the economic loss is almost in tune, but the main problem is the vulnerability of human life in the Asia Pacific zone, whatever we have seen in the last many, many earthquakes. Now we have compared, one slide was not showing, I don't know, the summary of our study between the Haiti earthquake in 2010 and Japan earthquake in 2011. Haiti earthquake was only Richter scale 7 scale, and Japan earthquake was 9 Richter scale. So it is a huge amount. And in terms of Richter scale, the energy release is almost 1,000 times. If it is from 7 to 9, 31 times for one scale up, 7 to 8, 31 times, 8 to 9, another 31. So 31 into 31 is almost 1,000 times more energy released during the Japan earthquake. But if you see just the death, more than 3 lakh people died in 7 Richter scale, whereas around 16,000 died in Japan earthquake, including the secondary effect of nuclear radiation. Now, why this has happened? Because one major issue is the focal depth. It was only 10 kilometers. Yesterday, Turkey's earthquake was 18 kilometers. So one thing is focal depth. Another thing is the duration of earthquake. That also plays a significant role in case of seismic disaster. And our contribution is the proper design construction plays a major role in creating huge death and loss. So it has been summarized that underdeveloped country, they have suffered more casualties and damage because of the design construction practice, governance, material quality, vulnerability mapping, etc. And all these things we should consider in a probabilistic manner, because earthquake is uncertain, your material is also uncertain, your structural design component, there are a lot of uncertainties. So we should deal in a probabilistic manner. Now mitigation means seismic now there is a lot of word on mitigation engineering or disaster mitigation. It is not a foolproof system, but it is an effort to lessen the impact of disaster. In case of seismic disaster, we should do some exercise so that the effect of disaster is minimized. So there is a famous disaster mitigation cycle. After a disaster, there will be emergency recovery. Then people will think how to prevent it or how to mitigate it. And we start our preparation. But what happens after sometimes again we forget everything and we are waiting for another disaster to come so that we are again initiated, excited to do something. Now, I think disaster mitigation is supported on three pillars: prevention, prediction, and preparedness. And depending on the type of disaster, these three pillars will come into play. In case of seismic disaster mitigation, earthquake cannot be prevented. It is impossible to prevent the earthquake because it's in huge scale, it's a natural the event. The prediction of earthquake is also very with low confidence or not reliable. China has predicted once very correctly, but then they have uh, wrongly predicted after several earthquakes. So many researchers are working on this prediction, but still it is not a reliable technology to predict earthquake. Like cyclone prediction is very accurate, and now everybody knows that. So we have only one pillar left, that is the preparedness. So as we are prepared, then we will be able to succeed in mitigating the seismic disaster to the extent possible. So how to uh, prepare ourselves? Anything, whenever there is a problem like COVID is a disaster, then what we have done, either we have to reduce the seismic hazard or we have to increase our performance. In case of COVID, we are uh, staying in the house. We are uh, we are not going outside. So these are the reduction of hazard. The chances of COVID is less. And again, when we are going outside, we are using mask, we are using sanitizer, we are taking vaccination. These are the improvement of performance. Similarly, in case of earthquake, to prepare ourselves to mitigate the earthquake disaster, one is reduction of the seismic hazard and another is the improvement of the seismic performance. For the new structure, there are ample scope, ample suggestion in the codes, and codes are also going to be revised how we can do a structure more earthquake resistant. Simply, if we make our structure lighter, then because earthquake is not a direct force, it only gives a acceleration at the base. So depending on the mass of the structure and as per the famous laws of motion of Newton, P is equal to mf. So the force experienced by the structure is nothing but the mass of the structure multiplied by the acceleration caused due to the earthquake. So one of the common example, one of the easiest thing is to reduce the mass. Like Assam house or Sikkim house or Ikara house, these are the traditional house made of wood, bamboos, etc. They are very good in taking tension, but at the same time their weight is very low. So nature is also developed the material for trees, etc. They are much more ductile, but at the same time they are also very lightweight. So reduction of hazard is important. And there are a lot of structures we have already made, including the historical structure. They need upgradation or retrofit in the preparation for disaster mitigation. So in case of seismic consideration, the main three responses are: one, displacement; another, the velocity; and third one, the acceleration. Any one is, if we able to measure, we can derive the others either by integration or by derivation. So it is better to because the error in integration is less compared to the derivation, so it is better to measure the acceleration so that we can easily derive the velocity as well as displacement. But what are the main characteristics of earthquake? Number one is the amplitude. What is the peak amplitude, peak ground acceleration, or whatever acceleration or velocity or displacement? So that is called the amplitude, the maximum value, and from which we get the Richter scale value. Then the duration, then the frequency content. These things are not yet directly incorporated in the codal stipulations, but we hope that it will come, because you see, If the duration of earthquake is more, then the demand for energy absorption is much more. Yesterday's earthquake was 45 seconds, and that is quite big. Even it is situated very near to the fault zone. Normally, what happens in the near field effect? Near field means within 15 kilometers for a active fault. Then there are the force is almost like impact type, and the duration is small. But if we go far away from the fault zone, then the same impact, same earthquake is converted into a more durable, more duration earthquake, but with less amplitude. Then another important thing, whatever our earlier consideration is, all the weights are assumed to be vertically downward due to the gravity, but earthquake or cyclone effect are lateral. In addition, earthquake is a cyclic, that means reversal of stresses will come into picture, and they create inertia to excite. That means the structure will going to vibrate. That means we have to take into consideration the dynamic action of any structure during earthquake. So in beside the geological parameters, we have to consider the soil characteristics, structural system, what are the material we have used, design consideration, constructional practice and materials. In India, it's a vast country. There are a lot of different constructional practice. Even the bricks are different from site to site. And the important thing now coming into in a big way, that is the maintenance and what is the present condition of the structure. We are not so good in maintaining or maintenance manual in normal structures like railways or etc. Now these are very preliminary things. I am not going into the detail of it. Magnitude means the energy released and which was measured in Richter scale. This is one type of, if we put some if you put some pendulum, not inverted, and in a time scale during the earthquake, it will give the signature, that is the seismograph. And from there, earlier days, from primary wave or secondary wave, we can easily calculate what is the Richter scale. But we should remember that Richter scale is a magnitude measurement scale. We, the structural or civil engineers, do not require so precision over Richter scale. But our objective is the intensity. That is, what is the effect of an earthquake, which was given in MMI scale, modified Marshall intensity scale, or UNESCO MS scale, but MMI scale is more popular, and that is given by a descriptive or qualitative manner, that if it is 9, that means serious damage to well-built structure, almost total destruction. I think yesterday's earthquake was more than 10. So only seismic resistant structure remains standing. One thing we must observe in the videos and pictures, there are many structures which are converted into rubble, but there are few structures still standing very nicely. That means the capacity of those structures to satisfy the seismic demand is much more. This is our location of India in the Indian-Australian plate, which is moving very slowly towards the Eurasian plates. And this is the direction of movement. And there are subduction, because when the Eurasian plate is very big, so it can't move that plate, so it is going below that plate, that is called subduction. And sometimes there is a slip which causes a release of energy and which causes earthquake. If we see the major Indian earthquake from last 200 years, so the Kutch, then the Bihar Nepal border, in Assam Shillong, in Himachal Kangra, there are repetition of earthquake. You can see Bihar Nepal earthquake in 1934, again in 1988, and again in 2011. So similarly, if you see yesterday earthquake, 1970 there was a big earthquake. So there are several earthquakes in that zone, and Turkey is an earthquake prone area. They have developed a lot of earthquake engineering. Still they are facing that type of disaster. So remember, our preparation should go to more higher level to prevent that earthquake disaster. Japan has achieved a lot. After 1994 Kobe earthquake, they have developed their cities, etc., to a great extent that normal or major earthquake is not causing so much of disaster. This is our Indian map. Uh, Now we have all knows that there is only 4 zones. This Maharashtra near Latur after the 1993 earthquake, though the plate geological features is not so active, but due to the due to the type of construction material of stone, there is a huge disaster in that Kilari earthquake. So that has been promoted to zone 2 or zone 3. So first zone 1 was totally removed. Now there are 4 zones, and uh, it is more correctly visualized by this seismic zone map. I want to emphasize this thing also, that is the location of an area with respect to the fault zone. If it is within 15 kilometers, then it is called near field, and more than 150 kilometers is called far field. Now, one thing is the focal depth. If this is the, I think my cursor is visible to you. This is the earthquake surface. Now, the energy is released inside the earthquake. So this is my focal depth or hypocenter depth. This is the focus or hypocenter. And just above the surface is called epicenter. We all know about epicenter. But along with the epicenter, this depth is important, because, and then there is another thing is how far your structure from that epicenter or hypocenter. As we are increasing our location of structure, if we see that the wave is coming in this direction, then the horizontal component is much more compared to the vertical component. So that is one issue. But if we go by the near field effect, the vertical component is predominant along with the lateral component. And the different things, whether it is vertical or horizontal, A means acceleration. The slide may not be very clear to you. I have taken from the book of Penalesis and Kapus. This is acceleration, this is velocity, this is displacement. But this is for the near field, this is for the intermediate field, and this is for the far field. You see the same earthquake in the horizontal region. The duration is very small. This is in time scale. Whereas the same earthquake in the far field, the duration is much more. So this, when the structure is situated very close to the focus or epicentral area, they will feel the earthquake as an impactized, sudden, huge force. But when a structure is situated far away, say 400, 500 kilometers away, then the same earthquake will be felt in a long duration but relatively small amplitude, whether it is acceleration, velocity, or displacement, whatever may be. Now, this is, I have already mentioned that this, in case of near field, it is impulse type. In case of far field, it is cyclic type. Here, the fault rupture direction is important in case of near field, close to the fault. Whereas in far field, the soil stratification, what are the soil types, how they are, what is the depth of those soils and properties, they are important. The vertical to horizontal force is much more in case of near field, whereas it is much low. And the velocity in the near field region is almost 10 times higher than the far field. Similarly, when we go by the equivalent seismic coefficient method, equivalent static earthquake analysis, then we go for the fundamental time period. So in case of near field, superior modes have more participation, but in case of far field, fundamental time period, fundamental vibration is much more important. So there are few dissimilarities when we go for a near field structure design and when we go for far field. The last one you see that is a earthquake of 6-second duration in the near field region will go up to 22 seconds. Yesterday earthquake was 45 seconds. Now you see that not only the duration, what is the effect of duration? Duration means that it is a time scale, so the energy released by energy experienced by the structure is much more in case of far field. So therefore, ductility come into a big way for preventing or for preparing the earthquake disaster mitigation in far field. Another important is this soil wave amplification. This is an example of 1985 Mexico earthquake. Just a minute. Sorry. This is the example of 1985 Mexico City earthquake. You see, one structure was built at this is university of some university which is in the foothills, and another one in the lake deposit. Sorry, lake deposit SCT, some post office building. Now, both are. I'm in a presentation. I will talk later on. So, this is a university building which is situated on the foothill zone, and this is a post office building on lake deposit. If you see the responses, this university building, which is very close to the epicenter, that is much negligible. Whereas the 350 kilometers away from the Mexico City, that epicentral distance, they experience a lot of amplified wave, and that is because of this clay deposit. So soil has also play a great role in the earthquake disaster mitigation. That was further clarified that this university building and this is the post office building almost 5 times increased. Now there are different hazard level which are described either by peak ground acceleration or by response spectrum or by time hysteresis. Normally, we now for zone 3, zone 4, zone 5, ductile detailing as well as these response spectrum analysis became mandatory up to certain height. Now for all height structure, and zone 2 up to after 12-meter height of a building, we have to go for response spectrum analysis. So I will go through little bit of that. Now this is another thing of that effect of an earthquake in the near field zone. If you see, it is in the East Europe one study that it is the focal height, and as the structure is going away from the epicenter, the damage in terms of intensity reduces. The main area, there is huge damage of intensity 9, then intensity 8, then intensity 7. This is because the acceleration in the vertical direction, y double dot means acceleration in the vertical direction, that is up to 20 or 20 kilometer. It is huge amount, but after that it gradually reduces. So the far field and near field, there is a huge difference in terms of vertical acceleration. Now normally, as per our IS 1893 2016, that is the latest revised code, we go for design basis earthquake. But at the same time, we have to consider that what is the maximum credible or maximum considered earthquake. For that, the structure should not collapse. So our basic objective is, these are the different performance level. But before that, our basic concept is that for this design basis earthquake, the structure should be fully structurally sound. But for maximum considered earthquake, there may be some structural crack, etc., or non-structural crack, but the structure should not collapse. Because if we go for a foolproof is not possible, but if we go for the design for maximum credible earthquake, it will be too much costly. So what we do, that zone factor, 50% of the zone factor, Z by 2, that we consider for the design basis earthquake. So these are the different performance level. Depending on the importance of structure, the performance is determined. Say for a hospital building or a nuclear reactor, it should be fully operational. So for that, the importance factor is much higher. But for other buildings like school building, etc., some important communication building, they should be operational. There may be some panic, but after the event, we should see that it is no problem. We can go there. But the minimum thing for any structure, including our own house, it should be life safe. That means there may be some cracks, but life should not be endangered. And finally, for the maximum credible maximum considered earthquake, this structure may be near to collapse, but it should not collapse like this. So it's a collapse prevention earthquake. So this is a picture from 2009 2011 9 Richter scale Japan earthquake. You see, they are making steel intensive structures, steel frame with infill concrete and walls. The structure was totally destroyed, but you see the structure is still standing. There are plastic hinges, but the structure has not collapsed. So this is a perfect example of a three-storied building which prevented the collapse. Even the maximum earthquake came in the order of Richter scale 9.1. So many people ask that I am not going to deal with these preliminary things because time is going on. There are frame structure or wall structure, shear wall, or it's a combination of core wall, shear wall, and frame. So that is called dual structure. These are the unfavorable plan. These are the favorable plan. Like nature, symmetry is very much preferred. And if we go by symmetry, there are a lot of earthquake vulnerability to be reduced. Not only in plan, but also in elevation. These are the unfavorable, like heavy mass at the top. So like any hill, it is like this, nature like that type of structure, so that the CG is at the lower level. If there is a plaza type of structure, make two separate structure and give a seismic gap in between. The column should not be floating one, it should continue up to this. And in case of two build structure, this connecting portion should not be rigid, it should be flexible, so that the incompatibility between the two structure when they are vibrating in different phase, that is not suffered to this small structure. So it should be flexible. On one side fixed, another side you may make a roller, so there will be reduced problem. I'm not going into detail, but one thing everybody knows, but still I want to say that strong column, weak beam is preferred. Why it is preferred? Because we do not like that hinges to occur in the column. Column failure is a global failure, beam failure is a local failure. So therefore, it is intentional in the design aspect that beam may crack or hinge and then column. So local failure is preferred over global failure, so that strong column, weak beam concept is a very simple one. There is another issue of ductility. This ductility, there are two types of ductility. One is material ductility. We all know about that. Steel is more ductile than concrete, but that is not the end. In case of structure, we need structural ductility. Even if we make a structure with steel, it may be, the structure as a whole, it may be brittle. So what is ductility? Ductility is the inelastic deformation capability. It is not in related to strength or other things. So if a structure is very strong, but and the E value is also very high, but after certain times it breaks, that means it has no plastic deformation. So it is a stress strain diagram of a brittle material. Now when we go for ductile material, the strength may be little less, but it has a plastic plateau and then it is strain hardening. So like mild steel. So what is the basic difference is the area under this stress strain diagram, that is the energy absorption capacity. In one word, it is called toughness. So toughness is provided by the ductility, which is actually the energy absorption capability. And during earthquake, we have seen, particularly in the far field zone, and in India, most of the areas are under the far field zone. So we need a lot of ductility to prevent our structure from total collapse during a maximum earthquake. So ductility has a great role to play. And there are two types of ductility in structural case. One is global, another is local. Local means in the members concept, and global ductility is the total structural concept. Now, if we consider a portal frame, now when there is a huge story shear, then it will go some deformation. And that deformation, if we plot with the increase of height to the total deformation, after this elastic, ductility is basically the inelastic deformation capability. So by any means, whether it is concrete structure or steel structure, we have to provide the detailing in such a way that inelastic deformation capability of the structure increases till it fails. So ductility factor is decided by the uh, failure deformation, by the yield deformation. And there is a concept that if we go by the equal maximum deflection concept, so if it is a brittle structure or the linear structure, it can take this, you have to design for this amount of force, then it will go by this drift. But if we go by this elastoplastic model, then for this is the yield deformation, we can get a structure like this. It is idealized structure for this amount of equal deformation. But that will not serve the purpose for energy absorption point of view. So what the exact thing is, the area under this linear behavior, this triangle area, if we equate with this trapezoidal area, initially it is a linear and then plastic deformation, inelastic deformation. So this area must be equals to this area, then only with the reduced force requirement to that from D to C, we can easily design the structure for a very low force, but same or equivalent potential energy aspect. So that is the requirement of ductility if we are designed for maximum considered earthquake to the design basis earthquake. But at the same time, we want to protect our structure. It should not collapse. Even if there is a huge maximum earthquake comes, then only possible for a small design force, economical design, but we have to provide the ductility to that extent. And again, another one thing, it's in case of structure, there will be a critical load path during earthquake. So all the members in that critical load path must be ductile in material point of view. Anyone, if it is brittle, the total structural ductility will be governed by the weakest link, that is the brittle link. So we have to be very cautious, and that is only possible by the non-linear analysis, what is called pushover analysis. Then we can easily identify where are the deficiencies and how to improve the performance so that the structure is mitigated during an earthquake. Now, these are well covered in our IS 13920 2015, and I think we all know, but still the most important area are the joints. Most of the structure fails due to the weak joints, not due to the weak members. So the joint, particularly in reinforced concrete structure, the development length is very, very important. While we are going to construct something, we must give enough importance to see whether adequate development length is provided. To ensure in a much better way, the code has prescribed that not only the development length plus 10 times the diameter of the bar should be provided so that the joint failure is avoided and there is no chance of brittleness. So ductility is improved. Similarly, when there is some lap, the lap must be covered with very closely spaced stirrup so that the brittle concrete is transformed into a ductile one by the confining effect of these closely spaced stirrups. If we go by the beam or column stirrups, then earlier one, this slide is earlier one, that both are 135-degree. Now code is little relaxed. One is 135-degree, another is 90-degree. दिस इज नथिंग बट वेन एवर वी गो फॉर ए जब रस्सी को थोड़ा बांधते हैं तो उसको एक बार दो बार देते हैं. सो ड्यूरिंग एंड शेकिंग द स्टीरअप्स में गेट लूज एंड दैट लूज्ड स्टीरअप is not able to confine the concrete. So brittle failure may happen. To ensure that there should not be any brittle failure, we have to ensure that the stirrups must be in position. They should not open up. And for that, this type of detailing has been prescribed in our IS 13920. Similarly, shear failure is brittle failure. We have to avoid the shear failure, and therefore, the shear zone, that is the support, there will be very closely spaced stirrups, about 75 or 100 millimeter center to center. In between, we may go by the normal shear design. But to avoid the shear failure, at the shear zone, ductile detailing is prescribed in the IS 13920. Similarly, some other areas, all the pictures are shown in IS 456 and IS 13920. And not only in the beam shear location, but also in the column shear location and lap location, we have to provide the stirrups very closely. One another interesting things, earlier days we are not providing the stirrups in the beam column joint because that there will be huge area, so shear may not be. But the problem is when there is a lot of shaking during earthquake, the concrete may get crushed and the concrete elements can come out, and that will create a kinking of that joint. Kinking means sudden collapse of those steel reinforcement. To avoid that, even if the concrete get crushed during an earthquake, it should be confined within that beam column joint. That is the requirement, that we should provide confinement reinforcement or confinement stirrups so that the concrete is confined in their location to behave in a more ductile manner. The same principle was adopted in footing. The column is coming. Earlier days, these reinforcements are not provided, but if we go by ductile detailing as per IS 13920, we have to provide closed stirrups in the column embedded in the footing to avoid brittleness in the column foundation joints. These are few real-life pictures during our study in 2011 and 2015 in Sikkim and Nepal. You see in those areas, they did, instead of going for closed stirrups, they even provided some area where more than 300 spacing is there. We have measured. And they have suffered, that was 6.7 Richter scale in Sikkim. And they have suffered a lot of damage. The verticality of the G plus 4-story building got lost, and there is no other option but to demolish the structure. So, and there is another crack in the soil, what we have noticed in Sikkim, that is in area called Temi. There is a weak tea garden, and due to the slope stability issue, there are a lot of cracks in the soil. You see, we have seen some of the construction going on there, and we have seen no 135-degree hook. There are a lot of cold joints. These few pictures are taken from Professor Murthy's area during their study in that Sikkim. They also studied a lot, and they went up to the Chungtham area where very near the location epicenter is there. The offsets, the wide, large opening of stirrups, the splicing they have done or the lapping they have done at the beam column joint, which is not good for good structural reinforcement detailing. But nowadays, this picture was taken from our Calcutta Newtown area. You see, people are doing, people are working with closely spaced stirrups, because nowadays concrete can flow. Concrete is self-compacting, so there is no issue of congestion, etc., like before. So we can follow the IS 13920 in a very nice way. Now, these slides are a little interesting. That earlier slides we have seen that steel is providing ductility to the concrete member, but sometimes concrete also can play a role to increase the ductility of steel structure. Now, American Institute of Steel Construction, they have developed one thing which is called buckling resistant bracing. You see, when there is a portal frame, when there is a horizontal force, so due to that force, these get under tension, but this is under compression, and compression can create buckling, particularly for the slender steel structure, because this lambda, that means the slendersness ratio, is very high because of the higher strength of steel. So sections are very thin, radius of gyration is very low, so L by R is high, so there is a possibility of buckling. And buckling is non-ductile, that means sudden failure can happen due to the buckling. So even if steel is very ductile in tension, but we have tested most of the steel in tensile test, but in compression, the same steel can behave in a brittle, that means sudden failure. So to avoid that, now as earthquake is changing, reversal, so the bracing which was earlier in tension, now they are in compression. So by this, bracing can fail in buckling mode, that is the non-ductile mode. And that is a picture during the North Ridge earthquake in USA. And you see that the bracing was totally buckled. Now it is of no use. You have to replace it. So they have developed this buckling restraint brace. So what is that buckling restraint brace? Nothing. The bracing was confined by the concrete. So if you see the section, the steel is, if we take a section, the steel is inside, and the outside there is a casing, and the jacket is filled with mortar, either concrete or concrete mortar. Now this is like almost like this. So with this jacketed steel member by concrete, the radius of gyration, because I is increased, polar moment of inertia increased, so there is no chance of buckling. So buckling is being prevented by providing concrete to the steel. So whenever there are forces, lateral forces, though it is under compression, but buckling is not happening, again the reversal of stress, there is no buckling. So by this buckling restraint bracing, the ductility of the steel structure is restrained, is maintained. So concrete is also has a great role to play for overall structural ductility improvement, performance improvement. Now I am coming to that, whatever I have said, that one of my ME student, he was given the impact of the last revision of our IS 1893 Part 1 code in 2016. So what is that impact? So he has taken a lot of buildings, 12 story, 24 story, 30 story, 36 story, and he has also considered the effect of the new building code, high rise building code, that is IS 16700. So up to what height the wind is much more governing than the seismic consideration. But I am showing only the portion that what is the effect of the revision of the codal stipulations in IS 1893 Part 1 for a G plus 12 story building, because after 30 story, 35 story, then wind is coming in a bigger way. But below that, the effect of earthquake is much more, particularly for zone 3, zone 4, zone 5, whatever maybe. If you go by zone 5, then further increases due to the effect of seismic vulnerability. Now, what are the changes came in 2016 compared to 2002? I know though many of the people are only studying nowadays this 2016, but the concept or many buildings have been designed earlier in 2002. Before that, it was 1984 code. So, importance factor that there is a change. The response reduction factor for shear wall, for normal wall, different detailing, there is a change. Now, the most important one is the dynamic analysis requirement now become mandatory. Almost for all the structure, only zone 2 less than 12-meter height, you may not do the dynamic analysis. But rest of the structure, because in our country, most of the area is zone 3, zone 4, and zone 5. And even if it is in zone 2, if the height of the structure is more than 12-meter, we have to go for dynamic analysis. That was prescription in the 2016 code. Then the design lateral base shear, there is slight change. Torsional irregularities, fundamental natural time period, also there is a change. And the same structure, we will see that the fundamental time period has been increased. Now, the interesting thing, even if the structure is considered to be less stiff, that is flexible, that means time period is more. So as per the famous that response spectrum, as the time period is more, SA by G will be reduced. So the total base shear will be reduced. But with some other parameters, we will see that even if the structure is considered to be little flexible due to the earthquake, there will be some cracks, so stiffness will be modified to little extent. But other parameters in the latest code, we have seen that all the requirements from drift, displacement, story shear, base shear, everything has increased. Now, how to model this URM in fill? Soft story, now that is not allowed. The moment of inertia and allowable soil pressure, there is an increase in soil pressure. These clauses are changed to a certain extent. In this particular presentation, I am showing this example between a G plus 12 story building as per 2002. If we design, what was the capacity or what was the demand for which we have designed, and now as per 2016, what are the requirements? And that's show that the requirement of retrofitting has a great role to play in coming days to avoid seismic disaster mitigation, to ensure seismic disaster mitigation. Now, this is a typical floor plan. There are two parts, left and right. We have the same building. One part of the left part, that is the structural plan that was considered. And this was modeled in, initially modeled in ATAPS, then in SAP. If you see the diaphragm action of the plan area, these are the details. The structural wall thickness, shear wall was provided 200 millimeter. In some area it is 300. The size of the column is 300 by 900. The grade of concrete is up to foundation to second floor is M40, then M30, then M25. And these are the structural slab thickness, 110 millimeter to 175 millimeter. This is the beam size. And now, as per the latest codal stipulation of IS 1893/2016, this moment of inertia, that is the stiffness, has been modified to 70%, and shear wall also 70%, beam has 35%. So, whenever there are cracks, it will create the stiffness of the structure to reduce, and that has been incorporated in the codal practice. These are also what is the height of the building, length of the building, breadth of the building, height of the building, floor to floor height, finish, whatever I have considered. All the details are given, but this is, both are considered in zone 4. Calcutta, though it is written in zone 3, but it is very close to zone 4. And I always prescribe that there is no certain demarcation line between zone 3 and zone 4. It is gradually changing. So if we go by zone 3, we have to be very stringent in other areas. Otherwise, many of the people are going, particularly South Calcutta, this Salt Lake and this new town, newly built area where I am staying in Salt Lake, they may be better to be considered zone 4 because there is a lot of geotechnical issues that has been described in some reports. So zone 4 was considered. Now importance factor more than 200 people, 1 became 1.2. So all these parameters are considered. I am not going into the wind data. Now these are done by response spectrum method. Normally we do by response spectrum. Time history analysis is very in very special case we have to go, otherwise it is not required. Now if we can see, this table is for G+12 building as per 2002 code, and this is 2016 code. Now see, the time period from 1.423 seconds has increased to 1.848 second. That means the time period is increased by almost it is more than 20%. So that is the structure is considered to be flexible due to the development of some cracks in the structure during an earthquake. That was the concept of stiffness modifier. The translation motion, their participation, x and y, and the rotation. Similarly, there is nothing much change, but only major change is their flexibility in the overall structure. Now coming to the comparison of story shear, the red one is as per IS 1893-2016 and the blue one is as per 2002. Now there is a huge change in the story shear. These are the story level, story 4, story 2, 12 story. And if you see, there is a huge amount of change due to the provision of latest codal stipulation in both in x direction as well as y direction. There, as it is rectangular in nature, though the dimensions are different, so nature is almost similar, the values are different. Similarly, the overturning moment at the base, that is also increased from almost 7,500 to more than 11,000 for x as well as for y. In y, the overturning moment is more because of the slenderness in that area. So whatever we can see, that at all floor levels, both the story shear as well as the overturning moment increases due to the modification or the revision of seismic code. So that was the advances in so far our country is concerned. The story displacement, the story drift, they are also increased by a significant amount due to the revision of seismic code. This is only for 12-story building. We have studied also for the different higher story building, different other configuration. But I just want to show that the impact of this revision of code is adequately strong, and we have to cater that seismic demand very carefully so that the new structure is okay. We have to build with the newer codal stipulations. The existing structure may require retrofit to avoid the disaster. This is also the story dip, but this is for the wind. The top one is the stiffness of the structure, and that is x and y direction due to the seismic event. The lower one is wind. I am not going to consider the wind one, so I can skip this wind. But in a summary, if we see that the base shear, overturning moment, story displacement, maximum story drift, and story stiffness, if we see in x and y direction, this E for earthquake, W for wind. So if we only concentrate on the earthquake engineering, that is the today's topic, we can see that the base shear has increased to the maximum of 51%. The overturning has increased to the tune of 55%, 54.5. But the story displacement, that was increased by 128%, so more than doubled. Similarly, the maximum story drift, that was 150% increased, so it became 2.5 times. As there is a Flexibility, that means stiffness, has been reduced to the tune of 36.56% in one direction. So this summary can easily uh, it can be easily seen that the impact of the codal stipulation, not only from the fundamental mode and due to the other stipulations also, there is a huge increase, particularly in the drift and displacement, and a moderate increase in case of overturning moment and base shear. So now it becomes very mandatory, particularly for the urban area or for where the non structure was developed in a rapid manner without following the earthquake stipulation to that extent. Because if there is an earthquake like Turkey in our country, it may be Calcutta or it may be any places in the country, there will be devastation not less than their disaster. I think the disaster will be much more, because and to avoid that, the evaluation of a structure, including its age and its retrofit, becomes very, very important things. I am skipping the preliminary evaluation process as per IS 15 15 IS 1588. I think I have to check that code number, where the axial force, the shear, they can be easily calculated. Just measuring the number of frames, number of columns, etc. We can easily calculate. The codal formulas are there. And if it fails, then we have to go for the detailed evaluation, where not only dynamic analysis but also non-linear static analysis, that is the pushover analysis, is important. So there are different type of structural analysis, static and dynamic, the nonlinear pushover analysis, and very rarely we go by nonlinear dynamic analysis. Code-based design, we all know, that is the zone. I am skipping these slides, but this is the linear static method analysis, where the response spectrum is like that. So when depending on this normal formula is you have to calculate the time period of the structure, then SA by G we will get, and then the seismic coefficient Z by 2 I by R SA by G. R is the response reduction factor. Once AH, the coefficient, is calculated with the seismic weight, that is WS, that is the dead load, full 100% dead load plus some portion of the live load, and we will get the base shear, and that base shear is distributed in a parabolic manner, WIHI square by summation of WJHJ square, that is I is the floor. That was developed by this concept that if we consider a structure as a single degree freedom system and it is subjected to certain vibration, then the response is measured like A1 double dot, A2 double dot for different structure, and that is idealized like this. But when we go for the dynamic analysis, the same nature has been kept. This was the preliminary, this is the dynamic analysis. And then you see this is the response spectrum for 3 different type of soils. And once the time period for the infilled structure, that is the most commonly our building, it is a frame structure infilled with wall. Then this is the formula for time period. Once time period is get, depending on the soil where the structure is going to build, we will get SA by G. And that SA by G, we will get the force. But in case of response spectrum, we have to consider not only the fundamental time vibration, but also রঞ্জন, আমি একটা প্রেজেন্টেশন আছি, পরে কথা বলছি। Not only the fundamental time period, but also the other mode of vibration, and at least 90% modal mass to be considered. Then this is the mass participation factor, why IS 1893 was given, and these are the mode shape. So multiple degree freedom system, we have to analyze, we have to get the mode shapes, and as per the forces we will get the mass participation modal mass as well as mode participation factor. So they have to combine, then we have to combine these different modal features into one. This story shear, design lateral force at each floor is depend on the particular mode, kth mode. What will be the Z by 2, I by R, SA by G? SA by G is that particular mode. That time period is required. For that, we have to analyze dynamically what are the frequency, what are the mode shapes, and this is the mode shape, this is the participation factor, and this is the floor weight. So we will get different story. I indicates for the floor and K indicate for the mode. So then from story, we will get the total shear. And from this total shear, we have to consider by two method. This is the common complete quadratic combination. So there, if the modes are very close to each other, then this cross modal coefficient come into picture. Otherwise, if they are very well separated, then we can go directly by the SRSS method, that is square root of summation of squares. So then the cross modal coefficient is very low. Otherwise, this tuning factor, the damping ratio, beta is the tuning factor, that is the ratio of these two modes, J and I, and zeta is the critical modal damping ratio. So they come into picture and there will be little different from these to this. This is the general combination method, but otherwise for normal structure, regular structure, the modes are well separated and then we can go by this SRSS method. Means the V, whatever we calculated for different modes, we have to calculate, we have to square it, sum it, and then root over it. So we'll get the final response spectrum method. What is the base shear or what is the shear? I am little bit touching the pushover analysis, that is the nonlinear static analysis. And actually, what is the concept? It is a numerical analysis, numerical testing. The structure is being modeled and the base shear is increased incrementally. With the base increase of base shear, the story shear as per some predefined distribution, mostly it is taken as parabola, like I have shown, WIHI square by summation of that. So they are increased. So after, and we are measuring the master node at mostly at the CG of the roof. What is the displacement? So if we plot that in base shear versus roof displacement, we will get the pushover curve. But one important thing is we have to model the nonlinear of the material. Local nonlinear effect should be modeled, and that is possible in certain softwares. In that software, say for a very common and easy software is SAP, you can easily model in SAP that what should be the concrete property modeling, what should be the steel, what if you use some other material, that you have to model the nonlinearity. Then this increase of V, that is the base shear is increased, and what is the roof displacement, maybe some master node here. So this is called pushover curve, and you can see some sort of kink, and that is nothing but the formation of certain plastic hinge in some certain areas. So that will, whenever there is a plastic hinge, whatever happens, the material is going to surrender, that it can't take a load. So base shear is fault, and then again it is increasing. So, but another important thing, we have to consider displacement push, because after certain times the displacement is not proportional to the shear, but displacement is much more because of its inelastic in nature. So therefore, the base shear increment should be as per the displacement controlled manner, not a force controlled manner. So we will get the pushover curve. And if we plot this displacement versus acceleration, then it is called capacity spectrum. But by this pushover curve, we will get different hinge location, that is called weak links. What type of failure will happen? We can easily visualize that whether the hinges are coming at the column or at the beam. So if it is a strong column, weak beam, automatically beam will fail faster than columns. And we should ensure that the column, even if the column hinges are forming, they should form from the top to the bottom, so that the top story may get collapsed fast. But if at the initial stage, if there are hinges or weak links at the ground story column, then the total structure will collapse. And we have seen this thing in case of certain very soft story building. So these are the capacity spectrum, means base acceleration by displacement. Now the important thing is when earthquake comes, there are cracks, so stiffness is modified. At the same time, stiffness modified means time period increases, whatever I have seen earlier. Now time period if increases, SA by G demand will be reduced. At the same time, with the development of cracks due to earthquake, the damping increases. And with the increase of damping, as per the table, you see, we are normally for concrete structure consider 5% damping. So that is the normal factor one. But if damping increasing to 7, 10%, the demand, because of the damping, increase of damping, the demand of force reduced to 90%, 80%, 70%, etc. So the initial 5% damping was this envelope of SAYG. Now, with the increase of damping, it is scaled down to this, then 15% can scale down to this. And with the increase of time period, the spectral acceleration demand is shifting from this to this. So, suppose we are at this position earlier. Now, due to the time period increase, the demand for this type of soil is reduced. So, due to the development of cracks during an earthquake, the nonlinearity of structure plays a great role. So, number one, the time period increases due to the reduction of stiffness. Number two, the damping increases. And both have contributed the lessening of the seismic demand. And that seismic demand, if able to achieve with the capacity, this is the capacity spectrum earlier I have shown. Capacity spectrum means pushover curve is base shear versus displacement. But if I plot acceleration, base acceleration versus displacement, then it is called capacity spectrum. And the locus of this demand point, slowly it changes. So the locus of the demand points is called demand spectrum. And when this demand spectrum is crossing the capacity spectrum, performance point is achieved. That means the structure is going to perform, their capacity is more than the demand at this point. So the structure is able to withstand this amount of force or this amount of acceleration and with this inelastic deformation. So if we can provide that ductility that it can take this amount of deformation with that amount of force, then the structure is assumed to achieve that performance objective. Now there are different performance objective as per FEMA or as per ATC 40, but one thing is by this we can easily identify the weak links, the failure mode, and whether the structure is able to perform certain predefined objective or not. That can be achieved by pushover. But pushover is also an approximate method. It is visualized as the incremental static force of the real dynamic earthquake force. So if we want to see that, then dynamic analysis, either response spectrum or this time history analysis or shake table analysis is required. Now these are few examples that has been, it is a regular structure. One is I type of structure, and these are the pushover curves in SAP platform. And just I am going to show that the provision of one wall continue to the ground level instead of this type of only frame. What is commonly G plus 4-story building, bottom everybody is putting cars, so there is no walls. Now one is with wall, one is no walls. We can see that the force taking capability is increased by certain extent by only providing one walls. So if we can put some other walls, this increment can be more. Both in X direction from 1200 to 1480, from 1687 to 1898. All other parameters are also increased. Now, Now, I don't know how much time I will get. Hello? Can you hear me?
Yes, sir.
Hello? Yeah. How much time I can go?
Your scheduled time actually is over. It was on 1:15.
Oh, it's over.
If you
Okay,
want to take
I will
con-
close it by 5 minutes, please.
okay, sure.
Okay. So one way of the advancement, and nowadays there is a lot of going on in our country, is also base isolation, particularly for the heritage structure, steep structure. Base isolation is a very alternative solution, low cost solution. Earlier days, like Bhuj Hospital, New Zealand has supplied those base isolator, but nowadays in our country base isolator are being manufactured. So the huge earthquake demand of this red line can be reduced to this line. So this is the capacity we are designing for these code design force. This is the capacity, but with the if we increase the time period from here to there, then automatically the demand is reduced, and that time period enlargement of a structure is provided by the base isolator. It is nothing but a bearing type of structure on which the structure is being built. So this is what happened. This is a structure in Japan. 0.37 G was recorded at the base and 1.18 G at the top, whereas uh, a isolated structure, this was isolated structure, if you see, near about there is another building which was measured as 0.4 G instead of 0.37 G, but due to this isolator, only 0.12 G was recorded at the top. So instead of 2.5 time increment at the top, it is reduced by 2.5 times. So approximately 6.5 times force has been reduced by the introduction of this base isolation. So, but one important issue is that whenever we are shifting the period, that is the time period of the structure, no doubt the force is reduced from here to here. But at the same time, the displacement of the structure is increased from here to there. So there are certain restriction of the displacement due to the serviceability criteria and comfort consideration. So the shifting of period is reduced to this. So this is force displacement trade-off. You have to design within that force reduction to the displacement increment. So we are constrained by these two constraints. We have also designed for this our non-linear time history analysis for a 7-story building in structure in our eastern region, and we have also observed the same nature, that this is the fixed base structure which has increased from 0.475 by the Parkfield earthquake to 1.489, whereas base isolated structure has reduced to a great extent, like the Japan experience. But this was no doubt a numerical example, not measured. Similarly, for the other type of Shikkim time history nonlinear analysis we have done, where also 0.205 G acceleration was increased to 1.4 G for that roof level of a 7-story building, where there is no isolator. If I provide the isolator, it is reduced to 0.1. So there is a drastic amount of force reduction due to the incorporation of isolator. This is the summary. I am not going into the, but coming to the conclusion, seismic event is no doubt natural, but the disaster may not be essentially natural. And main reason is our incompatible design and construction to the seismic demand. Beside the geological, there are geotechnical, structural consideration, in addition to the governance and awareness that creates the huge disaster to take place. So the role of or the impact of seismic vulnerability and damage of RCC structure, design, construction, governance, material quality, vulnerability mapping, new technology, and the practice of that technology has a great role to play. Proper preparedness seems to be the most effective approach for seismic disaster mitigation. Ductile detailing of reinforcement is important for enhancing seismic performance of concrete structure. However, concrete may also enhance the ductility in case of steel structure by providing buckling resistant dressing. The seismic demand for high-rise concrete structure have significantly increased due to the latest revision of IS 1893. and there are revision to come. Seismic evaluation and retrofit of existing structure is significantly important and the need of the hour. And with this, there are a lot of distraction, but still there are hopes. People are working, people are researching. So more modification is to come. With this, I thank you for your patient hearing. I'm sorry that I have overshooted sometime. Thank you. Hello.
Yes, sir. I'm audible.
Yeah.
Okay. To all the participants, I will be sharing a feedback link in the chat box. So if you have any query related to sir's topic, you can ask over there, and we will mail that question to Professor Debasish so that he can get any that he can answer your questions related to your queries. Uh, Now I would like to thank you, sir, for this informative session and giving your valuable time to us. So we'll end the session over here. Thank you, sir.
Okay. Thank you.